So good morning, everyone. I'm doing a PhD right now at the Paris Observatory under the supervision of Benoît Mosler, the two co-supervisors, Boris Segret and Christophe Koppel. And today I'm going to talk to you about the BIRD technology that was introduced to you yesterday by Daniel Estroffer. So it's an autonomous guidance and navigation control system for interplanetary CubeSats. And I will be talking more about small bodies because we have different contexts, but this is what I'm going to focus on today, and the propulsive aspects for such studies. So the outline of my presentation, first I will introduce the different mission contexts that we are working on, and then I will talk to you about the trajectory correction managers, so the CM, that we need for our concepts. So describe them, compare three of them that we propose, and see how our control law can work on the CCM that is the most interesting one for us. And then briefly do a comparison of CubeSat propulsion systems for our situation. So obviously oops. Okay, it's not the final version of my presentation. What is this one? Anyway. So if we want to do a proximity operation, obviously our science case was inspired by the IDA mission, and with the AIM rotorcraft releasing CubeSat, 3D CubeSat in the vicinity of a system of asteroids like the most A and B. Our science case exactly is to do in-situ geodesy using radio science. So it has been said, different from what I expected, sorry. So as it has been said yesterday, to do so we need to do radio science between the CubeSat and the rotorcraft to measure Doppler shifts and ranges, so we can deduce the exact trajectory of the CubeSat and then find out some relevant information about the asteroid itself, its composition, its density, and so on. So from that, we derive some requirements for the main trajectory. So we need a low orbit and also a low velocity. Yesterday it has been said that we need something like 20 to 50 centimeters per second velocity and to be as close as a few kilometers from the main body. And we also want to have alternate of free-fall trajectories when we do science. So just be impacted by the perturbations, so the gravity field, and obviously also the solar radiation pressure, and then trajectory correction methods. This is what is shown in this graph at the right part of the slide. So we do some flying legs in the vicinity of the system. And in terms of GNC and AOCS, we want to be autonomous because we don't want to rely on the rotorcraft for our trajectory, and we also need multi-axis thrusters, or maybe gimbal with only one thruster, sorry, because we also need to control the altitude, and if we have electron wave on board, we need to offload them. And for the study, we take a fictional asteroid that has the same parameters as the Venus A, so with the 1.64 AU semi-major axis, and a diameter of 0.8 kilometer, and a mass of 5.3 10 to the power 11 kilograms. Okay, so the trajectory correction maneuver concepts. As I said, we want to alternate free-fall trajectories, segments of free-fall trajectories, and TCM loops. Why we do that is because with such small bodies, it's tricky to have to orbit them in a circular way, because the velocity will be very low, the period will be very long, and it's unstable because of perturbations such as the solar radiation pressure. So with this concept, what we want to do is, after having the science mode, if we, for instance, have a velocity of around 1 meter per second in one direction, and if we want to change the direction of our velocity, for instance, a 90-degree direction change, we have several trajectories that we can follow. Here we propose 3 of them. One that we will call a circular TCM, the one loop TCM, and the last one that will be more simple. And we just call it simple TCM. So they are actually, the circular one is just based on a constant acceleration with an initial direction. The second one, the simple TCM, is also a constant acceleration but with a non-inertial acceleration direction, which is fixed between the incoming velocity and the outgoing one. So it's a basic use of the two vectors. And if we take a look at the loop TCM that was imagined by one of my co-supervisors, it's basically a mathematical curve. It's a rosette, but only with some kind of four loop rosettes. And if we perform only one of those loops, we can notice that the position of the beginning of our TCM is exactly the same as the position at the end of our TCM, which can make a lot of things quite simple. And from that trajectory, we can derive the acceleration that we need to do it. If we compare the 3 possible TCM with the assumption that we have 3 CubeSats and no perturbation for now, because it is a very preliminary study, what we can see is that we have a shift here in the plane. We have a horizontal shift and a vertical one for the circular and the simple TCM, which we do not have with the TCM loop, which make things way simpler in terms of mission design, especially because we want to be autonomous. So it's good to know that we don't have to rely on the Earth determination while we are doing our TCM, because we know that at the end of our TCM, we follow that trajectory. We will do exactly at the same point as at the beginning. And it also optimizes in terms of space what we are studying, because we're not losing space while doing our TCM. And also, it's interesting to compare the delta D budgets needed for all those trajectories. We can see that the simple one is the best one in terms of delta D, but that the loop TCM is quite good compared to, for instance, the circular one. And in terms of first needed, the loop TCM is the one that requires the less thrust. So it's good also for very small electric for CubeSats. Here is the control law of actually that TCM. So here you have the figure on the top right. You have the figure of that TCM. So the acceleration, the angle of acceleration in blue in the diagram on the left is actually the angle alpha on the figure. So between the velocity of the CubeSat and the direction of acceleration that is needed from the trajectory. So we can see that it does not vary that much during the trajectory. So if, for instance, we need 1 day to do such a trajectory, it's easy to follow the good direction, because if we only if we just in the range of 65 to 115 degrees. And in terms of thrust value, we also need to modulate it during the TCM, but only about 25%, which is very easy. In terms of, during the maneuver, we see that we definitely need 3-axis control. So this is something that, as I said, we can do it quite easily because it's not too fast. And since we want to be on the 3 CubeSats, we still have to have a low power consumption, so less than 10 watts and a volume of less than 1 unit. Now, if we take a look at what exists for CubeSat small propulsion systems, here it's just a brief overview. There are a lot of them that are missing, just to compare some performances. we can see that if we want to have, so we will have the x-axis is the delta budget, and the y-axis is the mass ratio, so the mass of the power system over the mass of the spacecraft. Obviously, we want to use less than a third of the mass of the spacecraft, so not more than one unit, sorry. So it will be less than 0.3, the interesting zone, and we want to have at least 50 meters per second delta V, so we can perform at least 20 TCM during our mission. So few propulsion systems can allow to do that. There are many electric propulsion systems, like only on this graph, but you see that some of them exist, and there are some others in development that can also provide such performances. Here you have on the left for some electric propulsion systems, small electric propulsion systems, you have the performance. So the thrust to power ratio on the y-axis and the specific loss on the x-axis. So what you want is to have the lowest thrust to power ratio and the highest ISP. And if we consider that we have 3 watts. This was a previous study, but using 3 watts, what we get is that we will have for our specific TCM, it will take us, depending on the propulsion system that we use, between a fraction of days and up to 3 days to perform our trajectory. And also, we can see that we can do usually more than 50 TCM during our mission, which is quite good for our study case. So, how to conclude that? I want to remind you that this is a preliminary study, that we are focusing on how to investigate, how to study, a small body using those kind of TCM. So we want to make the mission design as simple as possible for CubeSat. So we have identified a TCM that is interesting, that is actually minimizing the shifts due to small propulsion, and also that the control laws that are coming with it are easy to implement. We have also noted that there are already existing small electric propulsion that can provide the required performance. Now, what we want to do is to have more simulations taking into account the saturation due to also radiation pressure and also the gravity field of the asteroid. And we are also planning some tests on a frictionless bench. So we could test this kind of control loop for such trajectories using gyroscopes, friction with propulsion system. But we are still to be decided exactly which one, but we already have some ideas. And this is what we want to do next. Thank you for your attention, and I'm sorry that wasn't the presentation I submitted the last one, so some slides missing. If you have any question, thank you.
Okay, we'll take some questions then, please.
Just one question. This study of the low thrust is taking another thruster than the main one in the BIRDY-T?
No, for now it's only we only consider one thruster, but we are not taking into account how to control the altitude. So for now we are considering using reaction wheels to control the altitude during maneuver. That's answering the question.
Yeah, because yesterday
the
BIRDY-T was using DEEE, right?
Yeah.
So why you cannot use that system for for this small delta V, so you need another one, or you can work with that?
No, we can work with that. At the beginning, actually, we were working with a consortium called BIRDY-T, which is doing plasma associated, but with some kind of liquid oil, and that could provide actually 4 axes of thrust, because there was one tank providing propellant for 4 nozzles, so we put as to control as well with it. And in terms of performances, here we fixed the trajectory duration at 1 day, but if we have more thrust, we can make it just shorter in time. So just a question of how much time we have to do that. Then we'll have to compare with the perturbations, but they will be very low because it's a very small body. So now at the first stage. Thanks.
Any further questions? No? In that case, let's thank our speaker again.